Hey engineering students, welcome to week 22A, and this week we're only going to have week 22A. There will be no week 22B. This week we are just going to do one video because we are going to give you a little breather, going to give me a little breather as well as we get ready to transition to our new unit. We have some robotics and coding coming up, which I have been telling you about. And so I just need a little bit of time to transition for that. And we're kind of getting to the end of what I wanted to do anyway. So this is well timed. It also gives me a little bit of a chance to work with the two projects that we have. So as an update on that, the Gil Addison project, I need volunteers from that team. You guys know who you are, to stay after school this week. I'd love it if you could give me like a half hour or even an hour somewhere this week. I need help with putting on oil, like a protective oil, with sanding, and then also with assembly after that's all done. And if I could just have a few of you do that for a couple of hours, let's say a few hours in total, we can have that easily wrapped up this week. And it's looking great. It works really well. At least I hope it does. I haven't put an iMac on it yet. Hope it does. And then I can keep on giving my attention back again to the Krista Jones project so we can build and deliver that. Now, also this week, you're only going to have a multiple choice Google Classroom quiz. We did one of these last semester, and I might just try that format again instead of the traditional like kind of paper scan send one. This will be just the multiple choice quiz style. So there's some advantages and disadvantages to that. It's going to be a little bit broad in its knowledge, so grab your notes, but I hope that's a little bit of a break for you. Make sure you realize there are, as usual, there are going to be 2 skill levels, so make sure you pick and submit the right one. Okay, that's probably all of the housekeeping. I think I want to jump right in. It's going to be a little bit of a shorter video, and we're going to talk about stress and strain again. Before I do it, let me give you the briefest of brief recaps. I've done this before, but I'm going to do it again. I know this is potentially confusing stuff. It's new, potentially confusing. Stress is defined as force divided by area. Strain is defined as the change in length compared to the original length. And Hooke's law in this new kind of version is stress is equal to the Young's modulus times the strain. Okay, that's how they relate. And then these first two are how those formulas are actually defined. Okay, so let's jump on in. Let's see if I can scroll down. The computer's been a little bit slow tonight. I wanted to show you, firstly, this is the kind of equipment that you'd be looking at if this is what you did, in a workplace career situation. And if you ever interned at a mechanical engineering laboratory or something, you might very well be assigned to do some testing with equipment like this. I think this company needs a little bit more kind of Elon Musk, or even maybe a little more Davis Peterson in their marketing department. This is the TMI company, unfortunately named. Testing Machines Inc. is what that stands for, by the way. And they are a leader in innovative testing instrumentation for all industries. This is their model 8456. Nice, catchy, easy to remember name. Again, I think Musk has some advantages with his Dragon capsule and his Raptor engines and things like that. But no, this is the model 8456. And this is like a desktop version of some simple test equipment. Even this one, if I had to guess, I'd say this thing runs up to the $10,000 mark, but I'm not quite sure about that. It is new, as that lovely sticker implies. So imagine getting like a little thread of steel or carbon fiber or something. You'd put it between those 2 little metal blocks. There'd be like a little clamp of some sort to attach in there. And then this thing with its little digital readout is going to pull that apart bit by bit, and as it does so, it's going to measure those distances and then what forces it takes to get to those distances. Okay, and then it's going to compare them. Obviously one gives you your strain, one gives you your stress. Things that you would have to input into this machine as you get started would be the original length of the piece. It's not going to be able to tell that. So you would have to tell it the original length of the piece, and you'd also have to tell it the cross-sectional area of the piece. Again, it can't know that, but once you put that in, it'll be able to calculate stress based on the load divided by the area. Okay, so there's a little mini version for you. This one over here is more of the behemoth size, and still marketing department issues, model 8403. But this one you can see desktop computer there for scale. This thing is easily like about, I don't know, looks like about 6 feet tall. And you put your piece between the clamps here, and it is going to pull it apart bit by bit, and it's going to measure what's happening. Very strong control over the speed and the load and how quickly it is. Remember I said last video, you want these tests to be done at low speed. You don't want velocity of the action to become a variable. Okay, you want it to be very slow moving. So this does that, and this thing obviously is super strong, and you'll get great results sent straight to your computer. And I did tests like this when I was in university, and could have made a career out of it if I'd wanted to. I didn't want to. Not many people want to, but some people like testing stuff in labs. Material science also feeds into actually designing new materials, just inventing new types of things to do stuff what wasn't able to be done before. Pardon my grammar. Now, if you did use a machine like either of these two from the TMI company, you would have a piece. Sorry, this is very laggy. I'm dragging stuff around, and then it's happening about 10 seconds later, as you can see. You'd be using a piece something like this one here on the left. This is a computer model. This computer model has been run through like a virtual stress test inside the computer. But I want to point out a few things about what is going on. So we would take this and we would attach it into like some big grippy jaws, not to be confused with the giant mechanical shark that eats people. And this thing is going to pull apart with like a massive load. Let's just pick some numbers like we always do. It'll be way more than 1,000 newtons, but let's grab some nice round numbers. And this whole piece from top to bottom is going to be in a very consistent 1,000 newtons, like along its whole length, anywhere that you would slice this. Let's say that you could slice it through there. If you did that, you would find that there was 1,000 newtons of tensile force happening at that slice. If you were to slice it here at the thick end, there's 1,000 newtons right there. If you sliced it, let's say here at kind of the medium size part, there's 1,000 newtons happening there as well. So I want you to think now, as this piece, even though it's imaginary, this is exactly how a real piece looks as well. Why does the scientist, the material scientist, make this piece thicker at the ends and then narrow in the middle here? Why is that? Let's see how well you understand your physics and your materials science, your statics. Well, it has to do with this idea. Stress is force divided by area. Let's make up some numbers here. You can see how the cross section is bigger here. It's thinnest in the middle, and then there's kind of like intermediary kind of shoulder parts. I think those are actually called the shoulders. Let's say this thickest part, if you could measure it, let's say this thick part was like 500 millimeters squared. Let's say this part in the middle was like 100 millimeters squared. It's much narrower. Let's say this part here was, I don't know, 250 millimeters squared. You get the idea. Just like it's the smallest cross-sectional area right here. It's the biggest right here. And it's kind of a medium bare right there. Well, when you have the same force everywhere, because that's how force flows, force is always the same. It doesn't care about the size of the shape or anything like that. But when you have different cross-sectional areas, you end up with different stresses. Stress is force divided by area. So 1,000 divided by 500 gives you 2 megapascals. 1,000 divided by 100 gives you 10 megapascals. 1,000 divided by 250 gives you 4 megapascals. And by the way, don't forget, in the last video we said that if you mix newtons and millimeters, you end up with megapascals. It's not the same thing as our traditional way of doing things, mixing newtons and meters and getting pascals. These are all base units. This is kind of a modified base units method, but it works very well because things tend to be in millimeter dimensions. Anyway, but you can see what happens back to the main show. In this kind of long, slender middle part, you have a much higher stress resulting because of the smaller cross-sectional area. In fact, that is what the colors mean. That's what this colored graph on the side means. I don't want to get into the numbers because they're a little distracting, but the colors refer to stress level. The dark, deep purple, same as the tier that Santa Barbara County is still in right now, that is the lowest stress by comparison. And this kind of teal aquamarine blue, that is the highest stress, relatively speaking. So why do they design pieces with this like narrow then thick method? It's because it guarantees that the piece is not going to break, like right like here in the jaws. If you can imagine a test piece that by contrast was just like a straight cylinder with no variation anywhere, that thing could break anywhere. In fact, it would tend to crack and break where there was like a slight defect, or maybe like a defect in the casting or the working of the piece when it was made, or maybe like a bubble, like an air bubble. That's where it's going to break. It could break in the jaws, it could break in the middle, it could break anywhere. And that's not what we want, because when we maybe I won't do the undo because this is just going super slow. When we do these tests, the way we measure the strain, the stretch, is we actually put a little mark here and here, and then we get some kind of like electronic caliper system. I'm going to do like the analog version, but you get the idea. Get kind of like a little caliper system, and you mark 2 points, and then you follow those 2 points, and you see how much they stretch by on your gauge. And as long as it breaks somewhere in the middle between those, then the test is valid. It all works. It all makes sense. It was the region that you were looking at. If it breaks outside the region, that's kind of a worthless test. So these pieces are designed to create the highest stress right here in the middle, because the highest stress is where the action is going to happen. I hope that all makes sense. I hope it's not overly confusing. That's just kind of some interesting side information. And hey, maybe there'll be a little question on that in the quiz that you'll do later on. Who knows? I guess I know. I'm the teacher. Okay. if we can scroll. Oh, there we go. Let's see if it stays put now. Ah, I see. It's going to play that kind of game. All right. Okay, so now what we're looking at, this is, I think it's actually like fake data. I think this is generated from like a computer simulation, but it's pretty close to what the real life behavior is. So we are going to run with it. You're actually going to see in a little bit that I don't really trust these numbers, but the overall behavior and shape is totally fine. Let's look at what's happening. Along the bottom axis, it says tensile strain. So this is our Greek letter epsilon. And little quick aside here, notice the units they give to it. Millimeters per millimeters. If you were in Mr. Hertz's chemistry class or physics class, you'd be dying to cancel those out, wouldn't you? And to say, hey, there are no units left. Okay, that's why we say strain has no units. It's length per length, which leaves you with nothing. But I actually kind of like the fact that they have shown millimeters and millimeters. That makes sense. Okay, that kind of explains why there are no units. So that's cool. And I would have gotten rid of those green lines, but my software is not cooperating very well. So anyway. All right, on the... Oh, actually, sorry, before I go to the other axis, just to explain a little further. So when you see a value of like, say, let's say 0.3, what that means is the test piece has stretched 0.3 millimeters for every original millimeter of length that it had. Okay? 0.3 strain would mean you've gained 30%, is another way to think of it, 30% more length compared to your original length. These numbers in this graph are actually very high, these strain numbers. They're usually much lower than this. But as I say, I'm going to run with it, but that's a little high. Okay, over on the vertical axis, you'll note we are measuring things in megapascals. As we do, that's our standard kind of unit for this kind of work. It is a tensile test. It says that there, not compression. Tensile test. And I think that this was a piece of steel, although, again, the strain results make me doubt that. But I think it was supposed to be steel from the website that I read. Okay, starting off, we start the test right here with coordinates of 0, 0. 0 strain, 0 stress. This is like the zeroing out of the experiment. You put the thing in the clamp, you probably actually give it like a little pull just sort of get things started, get it seated, let it slip and catch if it needs to, let the jaws dig in a little, and then you press the 0 button and you say, all right, experiment starts now. And then what we see is very much what we talked about. We see what is essentially very close to, not perfectly, very close to linear behavior. If you forget all the red jumble, if I could instantly go boop and make that go away, what you can really see is a linear graph, y equals mx plus b. But even easier, there's no b, okay, because it starts at 0, 0. It's a y equals mx graph. In fact, it's what we've been talking about. This is stress equals Young's modulus times strain. Stress is the y, Young's modulus is the m, the slope, and strain is the x variable. Okay? This is just a super cool example of stuff you've been doing since middle school, but, you know, like in a useful, practical, like this is how they design the materials that your bicycle or your car or your bridge are designed using, like these principles. And it's the simplest of all principles, a linear graph. Now, what is the slope of this graph? M, M is slope. Well, you know that slope is rise over run. You know that we could say y2 minus y1 over x2 minus x1. Again, this is something you've been doing since middle school with Mrs. Smelly. And so I'm going to try to kind of pick a point. I'm actually going to try to line it up with the 250 megapascals right there. And I'm going to see if I can grab this ruler. I have a ruler tool. How cool is that? Let's see if I can make it go vertical. Come on. Come on. There we go. All right, now we're going to... Perfect. Okay, I'm looking for that, for where it crosses the bottom axis, if you're wondering what's happening. Right there. Oh, I like that ruler tool. Now you can go away. I'm done. Now, if I had to pick what that is, like where that crosses the line, I'd probably say, like, here's 0.1, so this is half of that. Really what we've done is maybe we've said like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, not perfect, but that looks like about 0.04. Okay, it'd be like 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.1. So this XY location is 0.04, 250. I might just get rid of that. Maybe that's a good way to get rid of those two. There we go. So we can pop these in to our y2 minus y1, x2 minus x1. We have 250 minus 0 over 0.04 minus 0. Okay, the one up here is the 2, the one down here is the 1. And 250 divided by 0.04 is 6,250. You can verify that on a calculator if you wish. 6,250 megapascals. You may wish to turn that into gigapascals, because once numbers get too big for the prefix you're working with, that's when you slip up or down to the next prefix. So that would be like 6.3 gigapascals. Okay, see how I did that? And now, because like every time you go up or down to the next prefix, you often just change your level of precision as well, like I did here. I could have said 6.25. Okay, so roughly 6 gigapascals. Now I'm going to say, this is why I don't think this is actually steel. When I first took a look at this, I'm pretty sure the website said steel, but I find that so hard to believe, because steel typically, no matter what kind of steel, has a Young's modulus of about 70 gigapascals, and this is like 6. So I don't know if I'm reading this graph wrong. I don't know if I'm looking at something that's like wood and not steel. These are like wood results. But the fact that it's off by very close to a factor of 10 makes me wonder if, I don't know, maybe I'm getting something wrong. If you spot I'm doing something wrong, please tell me. But this strain seems ridiculously high to me. All right. Now, let's keep this story going. That little mathematical area that we just analyzed with the nice linear slope, very well behaved, not perfectly, but very well. This is called, in the green writing, this is called the elastic region. Okay, like everything I just said there. Like this behavior zone right here is the elastic zone or the elastic region. It is elastic because in the truest sense of the word elastic, let's say that you are a mechanical engineer, you're doing this test, it's going great, but you're interrupted by, I don't know, your car alarm goes off, you have to go outside and fix the issue. Your wife calls, you gotta see what's happening. Your, tax man sends you an email, you gotta interrupt and talk to them. None of these are problems that I have, by the way. These are all good. If you turn off your testing machine and go and tend to whatever it is that you're tending to, and you kind of release the stress, release the force, let it go, this test piece is actually going to spring back exactly to its original size and shape with no memory effects of the action that you just did. It's not going to be any worse the wear. It's not bothered. It just bounces back just like a perfect cartoon spring does. Okay? Because you are working in the elastic region, the linear region. Okay? Elastic means it regains its shape after it gets deformed. Let me contrast that now. We get to this sort of level here. I don't know exactly what the stress is, but somewhere around, for this one, about the 275 megapascals mark, we get some weird behavior going. Look what's happening. It's going nice and smoothly, and then it's and it looks like a little Richter scale thing happening. In fact, the stress stays kind of constant-ish, around the 275 mark. But the strain is suddenly jumping. The strain is continuing to increase without any apparent increase in strength needed on the part of the machine. It's like it suddenly gave way, it suddenly slipped. And what we say is actually it yielded. The test piece yielded. It reached a yield stress. And for this particular material, our yield stress or yield strength, okay, symbol you might do stress with a subscript Y, appears to be around 275 megapascals. That's when it yielded. And when you cross into the yield instant, you've left the elastic, or you're leaving the elastic, I should say. You're starting to actually do damage to the piece. And, that's important to know. Because when you're designing bikes and cars and bridges, you don't want your pieces to ever be permanently damaged in a way that they won't spring back to how they were. All right, let's keep the story going. We now get into this kind of stuff here, and what is happening? It is certainly not linear. It is not, it doesn't appear very mathematical, and the strain is just huge for not really much increase in stress. At least way more than back in the elastic region. So this is the part of the story. This is the plastic zone or the plastic region. Now, plastic, what does the word plastic actually mean? In the technical sense, plastic has nothing to do with the actual stuff that we call plastic. I say that my ballpoint pen has a plastic barrel, all right, or my gear stick in my car is plastic. But really, if we're going to talk about the material those things are made of, that pen barrel, my ballpoint pen, is actually made of a polymer. Okay, some kind of polymer. There's thousands of polymers. The word plastic is actually an adjective. It's not really a noun. We use it like a noun, like this is plastic. This is a piece of plastic. But plastic is actually an adjective. So for something to be plastic, it's the opposite of elastic. When something is plastic, it means that you set it into a new shape and it stays in its new shape. As opposed to elastic. With an elastic object, you set it in a new shape, but whenever you let go, it's going to return to its original shape. We also use these terms actually in physics when we analyze momentum and collisions. Do you remember doing this? Maybe some of you are about to do this or are doing this. You have plastic collisions and you have elastic collisions. Sometimes we call them elastic and inelastic, but some textbooks call them elastic and plastic collisions because things don't bounce back to how they were. There's like car crashes, nothing's bouncing back to how it was. We are permanently deforming things. So such it is with the plastic zone. The thing has been permanently set into a new shape and arrangement. The molecules are in different alignments. It'll never go back to how it was. It is broken. You don't want to be there. Okay, keeping the story going. We get up to this place here, which if I were to kind of like measure back, appears to be somewhere around like the 480 megapascal maybe range, 475, 480. This is that guy we've been talking about all this time. This is the UTS, the ultimate tensile strength. Okay, or you can refer to it in this way as well. The stress subscript UTS. This is the highest stress that this thing will ever take. Now, I know that we kind of kept the story simple up to this video. We were sort of actually using the UTS as the design stress. I didn't want to get into it, but you actually don't ever do that, because if you reach the UTS, you are well deep into the plastic region. Your thing is busted. It's bad. You actually always want to stay below the yield stress. When I say below, I'm saying like well below, like 50% of it. 150 megapascals for this kind of material that we're looking at right now. 150 would be a great design stress. If you have a piece that is going to reach higher than 150 megapascals and it's made of this material right here, then you would have to make that piece thicker. You would say the stress is too high to do the job. I want to stay well in the elastic zone, so I'm going to make the piece thicker. Because remember, stress is force over area. You can take the force that's happening, you can increase the area, and that will decrease the stress. Okay, take the same force, increase the area, that will decrease the stress, and that can bring you safely back into an elastic behavior where nothing gets permanently damaged and everybody is happy. Okay, it still deforms, but it goes back when it's done. Okay, after the UTS, we get this weird behavior here now. This is very odd. The capacity of this thing to carry load appears to be diminishing. It is still stretching longer and longer. In fact, by the way, our UTS was somewhere around like here-ish. Like, I don't know what that is, maybe 0.42, perhaps 0.43. That means this piece is now 42% longer than it was when it started, which is wild. Okay, that's like, I think this is like a rubber band. This is not steel. This is some kind of rubber band or something, an elastic band. I don't know. It's stretching a lot. But anyway, at this point, the stress that it can carry is dropping, even though this thing is still stretching longer and longer and longer. There's a particular phenomenon going on here. I don't actually recall. I can't recall if I did this in the video or just in some conversations on the discussion board. But anyway, this is what we call necking. The piece is necking. And what this means, okay, again, here's that test piece being pulled, as we said. Well, after you pass the UTS, this thing is just miserably failing. Hold on. Try that again. All right. I did it a little dramatic, a little exaggerated, but the idea is there. Okay, this is the necking behavior. It actually kind of sucks inwards. And yeah, it looks like a neck, okay? These are the shoulders, this is the neck. And the area, the cross-sectional area is actually getting smaller and smaller and smaller. That's the reason why the stress appears to be getting lower, by the way. But I won't get too much into that. You know, the difference between engineering strain and real strain. Anyway, engineering stress and real stress, forget about it. But this is the necking region. And then at the very end of the story is the fracture or failure. Okay, obviously we're on the way to breaking, and this thing will suddenly go, and there's so much stored energy in this, so it will suddenly just go pop, and you get something called a cup and cone pattern, okay, where if you could kind of zoom in onto it, you've got on one side there's like a little, almost like a ball shape, and then there's like a matching kind of, you know, hole on the other side. So there's the cup on one side and the cone on the other, and that's always how steel breaks. If you look up pictures of it, you'll see exactly what I'm referring to. That's a cup and cone fracture, and so that's the very end of the story. The thing is broken. It is totally done. So let me summarize. I want you to make sure you get the big picture here. There will be some review questions on the quiz. Let's go through these things one by one. So first thing is that you always start off with elastic behavior that functions according to Hooke's law. This is where the Young's modulus actually applies and makes sense. And this is where you want to keep the piece. This way you want to keep materials for safe, long, useful life. Okay, this is the good place. The second part of the story is the yield stress. Okay, and that is where things get a little messy. Then we enter into the plastic zone, and the plastic zone is where you now will see permanent deformation. It will never return back to how it was after it goes through that yield stress moment in time. Then you have your ultimate tensile stress. That's the most stress that the piece can carry. And then the piece suddenly sort of sucks in very visibly. Like this is visible. This is not some kind of vague, is it happening? I think it's happening. No, this thing is like, it sucks into like maybe a third of its diameter. And then the last thing that happens is the fracture failure. Remember that when you design things, you really preferably want to keep your stress designs to somewhere about 50% of the elastic region. In fact, if I could go through, this is the happy place. When you get to yield stress, you're a little bit like, uh-oh, what? And then plastic zone, nothing good is happening. UTS, man, this thing is really pulled. Necking, you're kind of freaking out at this point. He's worried, he's not happy. And then fracture is just like, it's done. Okay, we're all done here. I want you to remember that, like, for all the things that happen, it's kind of academic. The only reason why you'd ever really consider the UTS even, and not like say half of the yield stress in the elastic zone, the UTS might be useful to look into, like if you had a situation where, you know, some crazy event happens, like, you know, maybe it's like a hurricane in a sports stadium and it's ripping the roof off, or it's, you know, like once in 100-year winds, you might be happy to design the piece so that even for that once in 100-year wind event, you stayed below the UTS, because at least the thing hasn't snapped through. It still is there. It's permanently stretched and damaged and deformed, but it didn't actually break and fall on anybody. Okay, so like most of the time you're in the elastic zone, but once in 100 years you might get a massive unexpected stress, and so at least keep that below the UTS, knowing that the roof's done anyway, and we need to go buy and build a new roof in that instant. Not what you want, but no one died. Okay, that's kind of common engineering thinking. We don't want this, but at least we all walked away. That's how this works. Okay, so we will stay in the mathematical zone. I think that's kind of it. That's a good place to leave it. Once again, look for the Google Classroom quiz assignment. Please, if you're on Gil Addison's team, you can put these in the discussion board comments if you like. Give me a day when you know you can stay after school, and I will make sure that I get you the stuff and set you up in our little outdoor shop. The weather's going to be much nicer this week. But that is kind of it. Thanks so much. Don't look for a second video. You won't find it. I know you're disappointed. Me too. But thank you for bearing with me. We'll see you guys around on campus.